So, let's finish chapter 27 is the plan for today. So we have finished the chapter, but we have to solve some problems as examples. And again, I want to remind you that chapter 27 is going to be heavily represented in the final exam. So you're going to have a problem from interference and the problem from resolving power of optical instruments. Yes.
Did you get a haircut?
Yeah, well, it's probably not material right now. We can talk about different hairstyles and everything else. We can talk about that after class. But I'm open to any other questions. Or if you're offering your services as a hairstylist, we can talk again after class. Okay, other questions? Yes.
For when our final is, are we just following the final schedule that's posted
We have to follow the schedule posted. And this means that everybody has to be in class. So no online final exams, only in class. And you're again going to have a choice. Do you want? Yes.
You cannot attend in person. Michael's thought.
So Michael, we have to talk with you separately about the final exam, but everybody else, we have to. I don't even have the right to change the schedule of the final exams. So you can attend the final exam of section 1 or section 2. It's not going to change anything, but you have to attend one of the two. And on the final exam, unfortunately, I'm not allowed to provide the assistance that we had for the midterms. Right, it is, but again, it is not going to be a final exam that's going to reduce usually. So usually you don't, at least in my classes, the final exam doesn't affect negatively the semester grade. You still have to do well. And if you remind me, the last week of classes, I'm going to give you the same formula for calculating the semester grade as we had before. Also, don't forget that brownie points matter. So go ahead and put your brownie point attendance in the Google Doc document. Okay, other questions?
What day is the final?
What day is the final? So
Monday, 12:30 to 2:30 if you're in this section, or if you take it Wednesday, it's at 10 to 12.
so you have two sections, and you can find actually, you can find the schedule. Where is it? So here is the final exam schedule. I guess. So this is spring. And the exam schedule should be somewhere here. Class schedule. Okay, let's look at different calendars. Let's go here. Academic calendars, final exam schedule right here. And in the final exam schedule, it should be low, but coming. So here is the exam schedule. And our class is,
I think this was for fall.
oh, is it?
I think it just, it says Monday or Wednesday, so I think it would just be Monday or Wednesday of.
Yeah,
of
let
final
me,
shoots,
let
so.
me. Well, in any case, this is the way to find it, right? So usually this section is, the final exam is scheduled for when? For Monday at noon?
12:30.
Yeah, okay, 12:30 for 2 hours, or around noon, let's say, if you want to start early. And for the other section, it is Wednesday, 10 o'clock in the morning. Usually, but again, the schedule is something that is selected for us, and we just have to follow it. Okay, so I see some problems on the board. I think that let's see what is problem number 12 here. Okay, so problem number 12. So you have a screen at some distance from a single slit. Slit means rectangular shape rather than circular shape, open. And you have a light with given wavelength and produces diffraction pattern. The width of the central bright fringe is given. What is the width of the slit? And look, this is a typical problem, just to remind you that if you have a rectangular opening like this, and the size of that opening, the width of this opening is W. In my case, in my version, they say that, well, this is what we're looking for, actually. And they say that you have some light here that is coming in, and the wavelength of that light is given. Again, for me, it is 559 nanometers. So it is 559 times 10 to the negative 9 meters. And here is the screen. They give you this distance, right? They give you the distance between the screen and the slit. So for me, just call that distance y equal to 0.54 meters. And now look what you have. Here is the central line. Always the central line is helpful when you're drawing diagram. By the way, all questions from this chapter, practically all questions from this chapter require diagram. So on the final exam, the diagram is going to be graded if it exists, meaning that if it is present in your work. So exercise drawing diagrams. From what I have seen in the last midterm, many diagrams where you have to form image from a lens, diverging, converging, many of them were not that good. So exercise drawing diagrams. Okay, so in our case, they say that the central bright fringe, the central bright fringe. I'm not showing the secondary bright fringes, but the central bright fringe, they say, has this size, this width. From here to here, they say is what? 0.055. Call that what? Call that. So we use the letter Y. Let's say this is the letter here is Z equal to 0.05. What is it? 55 meters. And they're asking us to find this. And in order to figure that out, you just have to use the formula for the angle at which you observe the first dark spot. The first dark spot is pretty much at the place where the bright fringe ends. So the first dark spot is going to be located right here at an angle theta with respect to the central line. And the formula that solves the problem says that sine of the angle at which the first dark spot appears is equal to the width. Actually, it is equal to lambda, the wavelength divided by the width. The wavelength of the light divided by the width of the opening. So this is the formula that we have. And now look how this formula is going to be related with what we have on the diagram. This distance here is given, the distance y. This is a right triangle. And well, if this total is 0.055, only this part is going to be half of it, 0.0275 meters. In other words, it is z divided by 2. And that's it. So now looking at this triangle, the formula on the board gives you the angle. This side is given. Solve for W. So let's do it. So you have that, let's say, the angle, tangent of that angle, let's say, from the triangle. The tangent of this angle is equal to opposite side, z divided by 2, divided by adjacent side, which is y. In other words, is z divided by 2 times y. And on the other hand, the sine of that angle is equal to this. So from z is known, y is known, you can say that the angle itself is equal to inverse tangent of z divided by 2 times y. And once you have this angle, you substitute it here and you get, well, this formula, you use this formula to say that the width that you're looking for is equal to lambda divided by sine of the angle. And the angle is already known. You can substitute it here and you have your width provided from there. So just substitute here the angle with what you got here. And of course, this problem can be solved without using tangent, inverse tangent sine, by making approximations, and usually those approximations are very good. So the approximation that solves the same problem in an easier way is approximation that looks like this. The angle in radians, any angle in radians, is the same as the value of the sine of that angle. And also it is the same, approximately the same, as the tangent of that angle. So everywhere where you have tangent or sine, you can replace that with the value of the angle in radians. So this means that instead of this formula, so this is valid only for small angles. And it is clear that the angle theta is a small angle because this is half a meter. This is what, 2 millimeters. So half a meter, 2 millimeters. Clearly, the angle theta is small and this approximation can be used. If you use this approximation, look what happens. Instead of sine, you say that the angle itself is approximately equal to lambda divided by t. This is the angle in radians, of course. Instead of tangent, you say that the angle again is approximately equal to z divided by 2 times y. And combining those two formulas, since the left-hand sides are equal, the right-hand sides also have to be equal. In other words, not d, but this is w, right? We're talking about width. So, right, w. So, combining those two formulas, it follows that lambda divided by w is the same as z divided by 2 times y. And therefore, solving for w, you get w is equal to approximately, of course, is approximately equal to lambda times 2 times y divided by z. So numerically, this answer and this answer numerically are going to be the same. At least as far as the accuracy of your calculator goes. Yes.
How come it's too wide?
So it is z divided by 2, right? This is z. For the triangle, it is z divided by 2. So I have z divided by 2 divided by y, and the rules for division of fractions says that this is the same thing as z divided by 2 times y. So this is where this factor of 2 in denominator happens.
If you just do z divided by 2 instead of that, would that be the same as z over 2y?
Yes.
Okay.
Algebra, well, this is not even algebra, but recall, this is tricky. Recall the rules for division of fractions. Z divided by 2 divided by y divided by 1. So do the rules for division of fractions, and this is, but of course you can do it in other ways either. So you can multiply and divide numerator and denominator by 2. You're going to, you're going to get that. Okay. So in all problems where you have this diffraction size type of questions, which are related also with problems that are talking about resolving power of optical instruments or the human eye, in all of those problems, this approximation is very good, and it is going to give you the answer without using inverse trigonometric functions and trigonometric functions at all. Okay. Any remarks about this problem? Okay, if not, let's see what is the next problem.
So 16 we did on Friday, but I think it made 0 sense to almost all of us. So that's why I just kind of wanted to maybe go over again.
Okay, let's go over 16 again, but let's first do problem number 13. Problem number 13. So a typical problem from resolving power of optical instruments, in this case, your eye. So you're looking out down from a height of 10,000 meters. The total of your eye is with a diameter of 2 millimeters. So those 2 millimeters probably have to be converted into meters so that all the units to be consistent. Determine how far apart 2 cars must be on the ground if you are to have any hope of seeing them as separate objects. In the case of red and violet light. So maybe the cars in part A are red, the cars in part B are violet. So this problem actually can be made a little bit trickier if they give you the index of refraction of the material inside your eye. Because you remember that when the light goes from air into material with index of refraction n, the wavelength. So here is air, let's say, and 1 equal to 1, and here is some different index of refraction. It has to be, of course, larger or equal to 1. But you recall that here, if the incoming light has wavelength lambda, the light that enters in the second material is going to have wavelength lambda prime equal to lambda reduced by a factor of the index of refraction of that material. So when, let's say, red light enters your eyeball, inside your eyeball, this red light is shifted to the blue part of the spectrum by a factor of n2. N2 is the index of refraction of the material inside your eye, which is of the order of 1.3. So the wavelength inside your eye has shorter wavelength, and as a result, you're going to see that the resolving power of your eye is a little bit better thanks to that. So in this problem, they don't provide the index of refraction of the material inside your eye, so you cannot take advantage of this effect. So you're just going to assume that the wavelength that comes from air is the same wavelength inside your eye. But in other problems, I think that effect has to be accounted. I don't remember which problem. Okay, I don't remember which problem exactly was the problem that this effect has to be taken into account. See, let me change the battery here so that people that are online to be able to. Okay, so now how to proceed in this problem? Actually, this is a typical problem from resolving power of the human eye, and you're going to have a problem like this on the final exam. So let's see how to handle this problem. So it is pretty much similar to the previous problem, with a little bit modifications. So here, so here is how the diagram has to look for this problem. This is the pupil of your eye. It is circular opening with given diameter d. For me, the diameter is 2 millimeters, which is 0.002 meters for my version, right? A millimeter is 1,000 of a meter. So here is the central line. The central line always is helpful. This is the rest of the eye. If you want. Here is the eyeball, but I'm going to look at the back of the eye as a flat. Otherwise, the picture is going to look very weird. So here is the retina, the back of your eye, approximately. It is approximately flat. For the sake of the argument, and to have a good diagram. Here is the first vehicle. Here is the second car. Well, you just have to imagine. So let's see. This distance, call that distance what do you want to call that distance? Call that distance y, equal for my version 10,000 meters. And now look, each of the cars is approximately point-like source of light scattered from that vehicle. And once that light goes through the circular opening, it is going to create in the retina a diffraction pattern. And the central bright spot looks like this, of course, the central bright spot of this diffraction. Most of the light intensity is going to be located inside in this central bright spot. So in other words, the picture of this car on your retina has this type of intensity. Yes.
So is the bright spot only on the top part of the retina? Or is that whole area that you've drawn?
It is the whole area. So this is just a central line to help me draw the diagram more better looking diagram. So again, of course, they're talking about airplane. So this means that the stuff is rotated again with the, so the down is this way. Again, it get used to draw pictures in a consistent way. Okay, so this is the image of the first car. The image of the second car is also going to be a diffraction spot of that type. And look, if the second car gives you a diffraction picture like this, the eye clearly can separate those two diffraction pictures. Clearly. The question is, how close the two diffraction pictures can be to be seen as separate diffraction pictures. Because look, if this comes very on top of this, you cannot see the two cars as separate objects. The two diffraction pictures have to be slightly separated. And the condition that is commonly accepted for to be able, the eye to be able to resolve the two diffractions pictures as separate pictures is the condition looks like this. The minimum of one of the diffraction patterns has to coincide with the maximum of the other. So the other diffraction pattern has to be not closer than this. not closer than this. And here it is. The minimum of this coincides with the maximum of this. And the same story for here. But you have to draw it so that it's here. The minimum of this coincides pretty much with the maximum of the other. So this is the commonly accepted condition to have a resolution of the two images. In other words, of course, this you need a second line to show the location of the center of the second diffraction image. And of course, the two lines intersect exactly in the middle of the pupil of the eye. So basically, they have. So you have to draw more carefully than I can, but they have to intersect in the middle. Well, not that matters that much because we're talking about this distance of the order of 10,000 and this distance of the order of 1,000. This is 5 orders of magnitude, 6 orders of magnitude difference. So this is very small, this is very large, which means that this angle is a small angle and our approximation is a good approximation. Okay, so knowing this, and once you have this diagram, you can immediately see that the angle theta, the angle between the center of the bright spot and the first dark spot, that angle theta is here and also here. And you know that for circular opening, the sign of the angle at which the dark spot appears is 1.22 times lambda divided by the diameter of the opening d. And the rest is just arithmetic. So here is the angle that we already calculated. And here is practically a right triangle, practically, with one side equal to 10,000. The angle is here. Figure out what is the distance between the two cars. This minimum distance that they call that minimum distance, what? Call it x. What is that minimum distance x? So from the right triangle, you can say that the distance x is equal to the adjacent side y multiplied by tangent of the angle theta, where angle theta has sign given with this. So you can substitute the angle here, the angle calculated from the first equation, and you're going to get the distance between the two cars. Yes.
Where's the 1.22 come from?
Yeah, this 1.22. So for a rectangular opening, the formula looks like this. Sine of the angle is lambda divided by the width of the opening. And we proved that formula in class using simple reasoning. For circular opening, the derivation has to be similar as for rectangular opening. However, it requires using of special functions, and in this course, we're not equipped with those tools. So this is a formula which comes for granted with no derivation, but the proof of that formula is similar to the proof that we provided for rectangular slit. Yes.
How did you come up with x equals y times tangent?
Looking at this right triangle, pretty much right triangle, by definition, opposite side divided by the adjacent side, opposite divided by adjacent, is equal to tangent.
Okay.
And therefore, only the opposite is y times tangent. So again, the first formula, you find the angle from the first formula. So from the first formula, you say the angle is equal to inverse sine of 1.22 times lambda divided by d. And after that, the angle that you obtain, you plug in the second formula and you get the result. Now, you again, if you use the approximation that we used in the previous problem, you don't need to deal with inverse sine and tangent. You can, so alternatively, you can say, since sine is approximately equal to the angle itself in radians, you can say the angle itself is approximately equal to 1.22 times lambda divided by d. And you can also say that the distance that you're looking for is approximately equal to y instead of tangent. Again, you can say times the angle. Angle has to be not in degree, it has to be in radians. In other words, this is going to be y times 1.22 times lambda divided by d. And here is your answer, numerically the same as this answer. Yes.
Do you care if we do it one way or the other?
You have to indicate that you're using this approximation, and you have to realize that this approximation works only if the angle is measured in radians.
So is it just safest to do the other way?
No, it is safest probably to do it this way because, well, it's up to you. But this is safer in a sense that you have to use your calculator less. And every use of the calculator comes with a probability for a mistake, for clicking on a wrong button. But you see how simple this type of problems are, and at the same time, those problems are important for practical purposes. Well, of course, not very often you're asked to estimate the distance between two cars when you are flying in an airplane, but exactly the same type of reasoning you use for estimating the resolving power of a microscope, telescope, optical instruments that you use. In the case of telescope, for example, instead of the diameter of the pupil of your eye, you have to use the size of the objective, if it is a refractor, and the size of the mirror, if it is a reflector. Okay, remarks and questions? Okay, so in the remaining, 8 minutes, let's go back and work on problem 16. But now it is your duty to ask questions so that problem 16 to be reasonable. So you have oil on water, right? They say wet pavement, which means that you have water on top of the pavement. They say that the refractive index of oil exceeds the refractive index of water. And this is important condition. So the film has non-zero thickness, minimum non-zero thickness, so that you have destructive interference of red light. Assuming that the visible spectrum is there between 380 and 750, for what visible wavelengths will the film appear bright due to constructive interference? So let's, again, diagram is very important. And look, if we cannot finish this problem again on time, feel free to leave and just look at the recording that is posted on YouTube, and you can find it using a search engine. So here is what you have. You have two problems. The first problem looks like this: red light in vacuum with lambda equals to 640. 640 nanometers in vacuum or air, right? This is air. Here, this is index of refraction, and 1 equal to 1 for air. After that, you have index of refraction N2 larger than the index of refraction N3. And after that, you have N3 is water. So this is oil, this is air, and this is water. With index of refraction, whatever is for water, 1.33 for water. So this is the first problem with destructive interference and red light. So again, the diagram is like this. Here is the reflected light ray. Light ray number 1 reflected. After that, well, of course, you have refracted coming here and getting reflected from the surface coming this way. And after that, getting refracted from the air oil surface and forming a light ray number 2. The thickness here is unknown thickness T. So from this information, and they are telling you that 1 and 2, light ray number 1 and light ray number 2 interfere destructively. From this information, you can find the thickness of the layer of oil. So let's find that thickness first. So first, looking for the thickness. Well, look. This light ray number 1, gets reflected from index of refraction larger than 1, larger than the index of refraction of the air, and therefore it is going to be shifted by lambda divided by 2. Well, let's say we're always, by convention, we're always going to think about not the wavelength in air or vacuum, but the wavelength by convention is taken to be the wavelength in the film. And in the film, the wavelength is going to be lambda prime, equal to lambda divided by the index of refraction of the film, which is N2. Unknown, you cannot calculate. Yeah.
Sorry, I got lost. Wavelength over 2 is because air has a lower index of refraction than oil.
No, always when you enter from air into some index of refraction, you always reduce the wavelength by a factor of the index of refraction of the second medium.
So where'd you get the wavelength over 2 by that first?
Wavelength divided by N2, N2.
For the first ray that was reflected.
Oh, well, this is not wavelength of it. I'm just telling you that this ray is shifted now by half a wavelength, shifted. It is not it is an effect that is described in the textbook in an analogy to the shift of reflection of a wave on a string. But this, we don't have strings here. It is just a rule which says that every time when a light ray gets reflected from material that has higher index of refraction than the first material, you always have a phase shift of half a wavelength. This is the phase shift of half a wavelength. So this is shifted by half a wavelength. This is what it means. Okay, so this one is going to be shifted. I don't know how to indicate the shift, but here, if the wave here was supposed to be like this, actually it is shifted by half. So I don't know how to draw it. Just maybe this curly line may be indicating this one is shifted by half a phase, half a cycle. Okay, the other wave, the other light ray that enters through the material, covers it, and comes back. The other one, look, the other one is reflected from this surface, but this surface has smaller index of refraction. Entry is smaller than the index of refraction of this material. So for it, there is no half a wave length shift, no shift there at all. But this ray number 2 covers more distance. The additional distance it covers is approximately equal to twice the thickness of the film. So the path difference between the path covered by 1 and 2, ray 1 and ray 2, is 2 times the thickness. But you did a phase shift of half a wavelength. So you say, okay, either minus or plus, usually the minus is a better choice. Lambda prime divided by 2. This is for the phase shift. And they say destructive interference, meaning that you have integer number of wavelengths in the film. This is the priming, where m is either 0 or 1 or 2 or so on. Well, they say the minimum. They say the minimum thickness. And minimum thickness is going to occur if you select m to be equal to 0. So 2 times t minus lambda prime divided by 2 is 0. In other words, you have 2 times t is equal to lambda prime divided by 2.
Last time you told us instead of m, it was m plus 1/2.
So we're going to get 4. Oh, you're right. I'm sorry. This is condition 4. Constructive interference. They say that the red light is destructive. So you're absolutely right. So it is m, the condition for destructive interference is semi-integer number times wavelength. So again, take m equal to 0, and you're going to have 1/2 lambda prime. This goes to the other side, and you get another 1/2 lambda prime. Yeah.
Sorry, so I understand why you got like the half the phase shift for the first ray of light, but why would you get half a phase shift for the second?
Here?
No, because like for the picture that you drew, is both ray 1 and 2 shifted by half a phase?
No, only this one is shifted by half a phase.
So, and that's the lambda prime that you're talking about? 'Cause I thought
This
lambda
is the shift. So
prime-
you,
I guess, why are you using the lambda prime and why not just lambda divided by 2? Because I thought lambda prime was the
yeah, look,
inside the oil.
you're right. This would be the right thing to do. But by convention, you always work with the wavelength of the light inside the film by convention. So you're looking for the relative phase difference between them. So it doesn't matter if you're talking about this wavelength or this wavelength. If you're consistent, if you work with the same wavelength, you're going to be fine. But by convention, you always work with the wavelength in the film. This is the convention, and this is the mistake probability is reduced that way, because you are forced to take into account that the light changes its wavelength when it enters a different medium. So this is the convention. I could have worked, but it's going to be trickier to work with wavelength in vacuum. So let's follow the convention and not bother. So this is, okay, once you have this, you can get the 2 times. So this means that this becomes, when m is equal to 0, you get that this is lambda prime divided by 2. In other words, lambda prime is like this. In other words, 2 times the thickness is equal to lambda prime, and therefore the thickness is equal to lambda prime divided by 2. This is the number that I got. But lambda prime is lambda divided by N2, the index of refraction of the oil that you don't know. Hopefully it is going to cancel. So this is the first result. It gives you an expression for the thickness of the film. And next, you have to draw a separate diagram for constructive, for the constructive interference of unknown wavelength. Assuming that the visible spectrum extends in this range, for which visible lengths will the film appear bright due to constructive interference. So now you have a different problem, and you have to draw a different diagram. So I'll clean a little bit of space just to emphasize that we're doing a different diagram now, different problem. Now you have, again, the same thickness of the film, and that thickness, we know that thickness. Well, not as a number, but we have analytical expression for that thickness. It is lambda divided by 2 times the unknown index of refraction of oil. And now you have a different wavelength, lambda 1 coming in. This is again air with index of refraction 1. This is again index of refraction of oil, that is, they say, is larger than the index of refraction of water. And this is again water. N3 smaller than N2. This is water again. This is oil again. And this is again air. Yes.
So just really quick, if I'm understanding this right, in the first part of the question, you're just trying to find the thickness for destructive interference.
That's
Now
correct.
you're using that thickness
Yes.
to find the wavelength for constructive.
Yes.
Okay.
Now the problem say it is the same film. It is the same oil film. So I'm using that practically, that it is the same film to have the same thickness.
Okay.
And again, you have the first light ray is reflected light ray number 1 again. The second one gets in, gets reflected from the other interface and gets out and gets refracted, and it is ray number 2. Pretty much the same picture, but now this is unknown wavelength lambda 1. This is what we're looking to figure out. This is unknown wavelength lambda 1. And again, the first ray is going to get a half a wavelength shift from the reflection from the oil surface. The second one is not going to get that because the water has smaller index of refraction than oil. It's not. And now the condition is going to look like this. The condition for constructive interference is going to look like this. The difference of optical paths, either minus or plus. I prefer to use minus. The wavelength lambda 1 prime divided by 2. This is accounting for the phase shift of one of the rays. The other one doesn't have it. Should be equal to integer number again times wavelength lambda prime of the first. Here, lambda 1 prime again is equal to lambda 1 divided by the index of refraction of oil, which is not known.
So, are you basically did the exact same?
Exact the same thing, except that here, instead of having destructive, I have constructive interference here.
Because you don't have m plus 1/2.
Yes, here I had m plus 1/2. Here I have only m. And m is integer number 0, 1, 2.
And at this point, we've solved for thickness, and so that's what's.
The thickness is given. I substitute the thickness here. Hold on. Let's do it. I'm looking for this wavelength. Let's write this expression in terms of that what we're looking for. So it's going to be 2 times the thickness minus the unknown lambda 1 divided by 2 and divided by the index of refraction of oil is equal to unknown number, integer number m times lambda 1 divided by 2 again. Okay, and now let's finish this problem right here. So we're 10 minutes over time, but again, don't criticize me about letting you go late. Right, the end of semester evaluations are coming, and any criticism actually is well, has to be fair. Right. Okay, so now this is the equation that we have. Just substitute the thickness T with its equal. So you're going to have 2 times lambda divided by 2 times N2 minus lambda 1 divided by 2 times N2 is equal to unknown integer number m times lambda 1 divided by N2. So this is the equation that we have. Yeah, you got it. And now this equation has to be solved. N2 is unknown, but it cancels out. You can multiply both sides by N2 and it disappears. A factor of 2 here disappears. And here is the equation that we're left with. The wavelength of the red light in vacuum is minus the unknown wavelength lambda 1 divided by 2 is equal to some integer number of wavelength lambda 1. So the unknown number is lambda 1, so you have to separate the terms that contain lambda 1. on one side of the equation, so move this to the other side of the equation. Let's say you're going to have lambda is equal to m times lambda 1 plus lambda 1 divided by 2. Factor out lambda 1 and write the right hand side right first. So lambda 1 times m plus 1/2 is equal to lambda. And therefore, lambda 1 is equal to lambda divided by m plus 1/2. And this should be your answer. So is it? Yeah.
It's just any integer that we want, right?
M is any integer 0, 1, 2, 3. So
Is there
if
one that's gonna be correct or?
maybe you may get more than one that is correct, but let's calculate the numbers for my version. Let's see if we're going to get, if you take m equal to 0, you're going to have, if m is equal to 0, you're going to have that lambda 1 is equal to 2 times lambda. In other words, it is 2 times 640. 2 times 640 is 1280, and it is not visible. So it doesn't count.
It needs to be between those two numbers.
It has to be, the answer has to be between those two numbers.
Okay.
So m equal to 0 doesn't fit. It is infrared wavelength, and we don't see it. So after that, if m is equal to 1, you have lambda 1 is equal to 2/3 of lambda, and 2/3 of lambda is a number that probably fits. So 2/3 of 640 is, well, you have to calculate it, but it is going to be hopefully the answer. And you may have another answer with m equal to 2. If m is equal to 2, you're going to have 2/5 of lambda, but 2/5 of lambda may not be visible light. Okay, so apologies again for.
Thank you for going over that.
Well, it is a long problem, but
Yeah, I definitely cleared some things up. We got through it the other day.
look, it is absolutely normal you not to get it the first time. And it is absolutely normal once you get it, you to forget. So don't be ashamed to ask a second or third time. Okay, see you on Wednesday.